I've got two of my favourite presenters back today. I always like talks on VHF propagation, and I beat up the propagation people regularly to say you need to do more about VHF. But fortunately, we have some really good work going on now. You saw some this morning with Tim G4LOH talking about combined modes. And the knowledge about Sporadic E is going up by leaps and bounds over the last few years. And I'm pleased to have Chris Deacon, G4IFX, and Jim Bacon, G3YLA, to give the next talk.
Right. Hi, everybody. Is this thing working okay? It seems to be cutting out to me, yeah? All right, I'm loud, 5 and 9. Okay, so Jim and I are both going to update you on some of the, what we like to call research that we've been doing, some of the experimental work and thinking that we've been doing about Sporadic E in the last few years. We've both presented in the last couple of years, and we're just going to want to update you on that. Before, though, I'd just like to give a little bit of background. So I'm not going to explain what Sporadic E is and all that. You're probably already very well aware of that. But who here remembers 405 line VHF television? Well, bloody hell. So they say the amateur radio community is getting older.
We've still got it.
Right, well, listen, those were the days when Sporadic E was economically significant. It actually mattered, and there was more professional work, certainly in terms of radio propagation via Sporadic E then than there has been. And these days it seems to be us who are doing it rather than them. But in those days, the BBC, I'm grateful to my friend John here for drawing my attention to this. This was an EBU, European Broadcasting Union project, which actually studied 7 or 8 paths for single hop Sporadic E over a period of 11 years. They started in the early 60s, finished in the early 70s, and they did it over 11 years because they didn't know at that point about the link between Sporadic E and the solar cycle. And they did some work on that. So those are the paths. This is all very old stuff, but it's still actually very relevant. So they found experimentally, this wasn't just dreamed out of some theoretician's head. And bearing in mind, of course, what they were trying to do was work out how often, what fraction of the time their television broadcast would be subject to those sort of patterning and noise that used to regularly come through in May, June, July, and August in those days. So they did some real interesting work on the seasonal variation of Sporadic E. The incidence averaged over that 11-year year period, which is pretty much what we would, what we'd expect to see. But they actually did it in a very systematic way. The error bars are the highest and the lowest in a particular year. They also did some work to correlate Sporadic E with the solar cycle. And we sort of know this, but there is in fact a slight anti-correlation between the incidence of Sporadic E and solar activity, slightly. It wasn't very strong. In fact, they only saw it on 3 of their paths, and 2 of those are northerly paths. So they only saw a statistically significant correlation in those 2 years. So in other words, Sporadic E is better at solar minimum. So it's actually been very good this year, because we're not far off solar minimum. So the longer the solar minimum, the better. That's right, isn't it? Have I got that right? Yeah. The other thing they did was look at the incidence of Sporadic E on time of day, and obviously that varies a lot. But they did see, they actually plotted just two of the years, but the sort of late morning peak and an early afternoon, an early evening peak at the midpoint of the path. So that's the kind of thing. Now, since the last VHF relay station in this country for TV went in the mid-70s, and of course the whole lot was decommissioned in the mid-80s. So this was like the swan song of VHF sporadic VHF TV. There is another piece of work they did in this report, which is about polarization, but I'll talk about that later because it's relevant to my part of this talk. So I'll now pass the microphone to my friend Jim, who's got some really interesting things to say. I think you can hang on to that. Oh, have you got? Oh, are you properly wired up?
I'm using the. Yeah, we're okay. Okay. No, I'll shout.
Thumbs down. Go.
I'll shout. I'll use them both. You can't, on the principle that you can never have too much bacon, we'll use we'll use both microphones. Now, a lady told me earlier on today that she thought there might be a... No, I'm not going but don't worry. We're all tucked up here. So this is going to be something about, for visitors from overseas, ask your friends from this country what that relates to. And Monsieur Le Poisson owes me another £5. What I'm going to do very briefly, because this is a shared event and there's so much interesting stuff going on with propagation that you really can't shoehorn this in very successfully and cover everything. So I've just restricted it to a couple of to the fundamental question of what we're up against. We all know that it's a difficult mode to track down, and for many years I've used this as my sort of maxim for how to say to people, don't just fixate on one thing as a cause for sporadic E, because there's a real probability that there are many things involved. I got involved because of the bit at the bottom of the screen here to do with weather. And the weather part contributes turbulence in the atmosphere, which generates atmospheric gravity waves. And this is upward propagating waves in the atmosphere, which have to move through the stratosphere to get all the way up to the E region. Things that will affect it, obviously, are the strength of the generators of the gravity waves. It's quite possible things in the middle here will affect the efficient propagation of those waves up through the stratosphere and towards the mesosphere and so on. And then you have this whole business up here, which is to do with the wind shear theory of sporadic E, which basically says that if you get gravity waves moving upwards to interact with the neutral winds in the E region, these winds have a certain characteristic. It's hard because you don't measure them. It's hard enough measuring weather at the surface. But measuring weather up there as a routine course of action is incredibly difficult. But there are tidal winds. It's not like a tide in water, but it's caused by the rotation of the Earth, so it's a tide. And the wind flow in the E region has a semi-diurnal component which is stronger in the mid-latitudes. So we end up with two peaks to that. Now that may have some influence on this bimodal peak for when sporadic E happens. And being a bear of very limited brain, I've kind of got myself hooked on the idea that if you imagine what happens, say, if you visited Western Scotland and visited the entrance to one of the many lovely sea locks and you saw the tide coming in through the narrow inlet, you would see a wave motion set up, standing waves on the surface of the water coming in when the tide floods in. And when the tide is still and it's turning and there's no flow, the surface is flat. And then when it goes out again, you also see the standing wave setting up. So think of that as a metaphor for what happens when these gravity waves interact with the background winds. And then you get to the problem of the actual making of sporadic E, and a lot of research from the professional side of ionospheric physics for many years has taken samples from within sporadic E patches, which comes up with a predominance of silica or magnesium, iron, and long-lived metallic ions. And this isn't the talk to explain exactly how all of that business goes on. But suffice to say, if you've got neutral winds in that level of the E region and you're blowing charged particles around produced by meteors when they burn up, then in the presence of the Earth's magnetic field, you can set up, because gravity waves do this, you can set up opposing wind directions at a relatively small height interval. So if you're getting a deflection through the tilt of the Earth's magnetic field downwards because of one direction, if you've got an opposite direction wind, you could be pushing the stuff upwards and you can converge it till it's a dense enough patch to give you ease. So that's the snapshot of that. And it's just to say this is what's the background to all of the good works that goes on when people log Sporadic E QSOs, the wonderful maps by Gabriel Sampol on dxmaps.com. Many other clusters are available. They're all equally good, and they're meat and drink to us. And it's really all about looking for elements that control it. Is there something that's more important than others? This is not about finding out exactly the mechanics of it, because we aren't up there with tools and tricks of the trade to do that, but we can, through being an amateur community with access to lots of reports, perhaps come up with something about the climatology of it. So looking back at what's happened in 2017 may allow us to do that. So over the last several years, since I started looking at this, the original red sky at night philosophy was that it was all to do with thunderstorms. That hasn't really stood the test of time. It does seem that the predominant the predominant association in the weather world is probably jet streams and the turbulence that they might create. So it makes a lot of sense to look at some of the longer term seasonal changes in jet streams. Are there any links, for example, between good years or poor years, or contrast between those? And we'll have a quick look at Europe. And this is how Europe looked during this summer. And what this is a collection of maps. Now, you don't need to get the detail other than to know Britain on each map is roughly in this location within the coloured picture. And oranges and reds are the jet stream. And this is an average wind flow, an average speed contour map of a month at a time. So this is May, June, July and August. And the point to come out from this is that we know that the months behave differently during a sporadic E season, and the distribution of mean winds as produced by the jet stream are quite often different. This year, very little going on nearby in May, weaker jet stream activity in June. You've got to understand that if you're making these gravity waves, this is where the E's will be. So ideally, you want them sort of down around here for the first hops. But August stands out as being a very much more active, a lot more unsettled weather. So it's one method we have in the armoury of having a look at why one month or one season might be different to another. Well, talking to Ian, got a wonderful subjective set of comments. We're all scratching around in our memory banks, trying to discover which years were better for transatlantic paths. And in Ian's sort of list of the last 6 or so, sorry, it was Chris. Yes, you are Chris. I don't know why I was thinking about Ian. I was talking to Ian earlier on. So 2017 and 2012 were his go-to years. Now, I've plotted the same contours going out across the Atlantic, and can we see anything different? Well, one of the things, this one, 2013, doesn't feature because it was a sort of neutral year. There weren't any strong signals one way or the other. 2014, 15 and 16 were both not particularly good. 2017 was good, and 2012 was very good. Now, what you've got to remember is, in a way, when you average over a season, this is now, we've moved to looking at the whole of the season from May to August, you're going to smooth out the individual detail and the curls and the whirls of the jet stream. So you end up getting a smear right away across. But it does seem as if you look at the position of the flow, very much the similar orientation for the 2 good years. And even in the mean pattern, you're getting some sense of undulation there, as if there were some semi-permanent troughs and ridges in the Atlantic pattern of the jet stream, which shows up when you average over a 4-month period. So that means it was quite a strong signal. And it's when you get the individual jet streams producing those curls that you can feature an idea that says, if it's strength of wind in a jet stream, turbulence produced by that fast flow, or in particular the entrance and the exit of a core of strong winds, then if you've got a very disturbed undulating flow, you'll have several of these entrances and exits and cores stepped across the Atlantic. So the idea that you can't have that many paths across the Atlantic to produce sporadic E is not necessarily valid when you look at it on a day-by-day basis. And for this set, which is looking at May, June, July, August, very much more active right the way across. So you could have some stepping points getting out halfway from that side, for example, in June, but not a very good link on our side, and so on. So it's worth further experimentation. So if this is a useful way of looking at things, then perhaps looking at the individual events is what we should do. So to do that, I spoke to Ian's friend Chris, and he's flagged up 3 dates when there was sporadic E early in the morning or mid-morning, early morning towards JA. So if this idea is going to work, we need to see what might be involved there. So this time I've decided to look at individual days within those 3 families. And here's the jet stream flow. Strong colours, the yellows are the strength of the jet stream. These coloured lines, blues and reds, represent areas where the pattern's changing rapidly. So it means either developing or moving quickly, both features that could produce more turbulence. And the magenta-y sort of orangey blobs are forecasts of severe thunderstorms. This is all from an American GFS model, which is freely available. There's charts of this on the web all over the place. We separate them out. This is for midday on the morning of the JA paths. And if you take the path to JA from here, you will see that you've got a very distorted, as we say, meridional, elongated pattern in the jet stream, providing stepping points where you could get some turbulence propagating up to make the E's. The second period, I picked a day within that, and there you can see a similar thing, still that very disturbed long meridional sort of diversion to the jet stream. So you don't get the same situation with a strong flow that's more zonal, but you need this. And if it goes across the top towards northern Russia, now I know where to look. I'll be biasing the maps a little bit further north on those days. And the third one, again, same thing. So it's coming up with some sort of sense that if the primary cause of the gravity waves might be to do with jet streams, it won't only be to do with it, but if it might be the predominant cause, then it makes a lot of sense for us as amateurs to look at where these jet streams are. So here's your test. Because you've all been paying a huge amount of attention here to what me and Chris Ian have been saying, where would you expect the E's to be on this one? Britain is here, southern Norway, Sweden, southern France, Alps here with some thunderstorms, jet stream through there. Where would you expect there to be some E's? Where you think the actual patch of E's would be, not where you're going to work, where you think? So you could look for places. Here's a jet stream.
East northeast, something like that.
East northeast is a good one. Who said east northeast? Don't. Yep. So this jet stream looks very good. One of the things that comes out is where jet streams interact with mountain ranges. It's like added bonus. So you do get the chance of rather more turbulence because of the disturbance of going over the mountain range. So that would be a good place, particularly with one of these lines showing rapid changes. So let's see what happened. And remember the little bit of jet stream off the coast of Portugal and down there. So here's where the big E's patch was, right on that main jet stream going towards southern Scandinavia. A little bit back here, further back along the jet stream. Some isolated paths down here, possibly to do with, now remember these are smooth model forecast plots, so these aren't the actual measurements, and the real wind will have much more detail and sharpness to it. So it kind of is a way to go, isn't it? Looking at, just as simple as looking at jet stream charts could give you a bit of a heads up on things. Now for the last few years, just very briefly, I've been preparing a blog on the RSGB forums pages where these jet stream charts are published every day. And during the season I write a blog, out of the season I don't, but we're going to move that to a new site soon, which will be propquest.co.uk. But for the time being, it's on the forums and on this site. And the format takes the shape of a 4-up set of charts showing how that jet stream pattern changes during the day, and a commentary to the right of it. But it strikes me that with all the different things from that first schematic of what might be involved with these, perhaps we can come up with a weighting function that sort of looks at all of those individually and has a think about, are all of these in place? Because any one of these could be a game stopper. It could take away the chance of ease. So you want to look at all of that stuff, and you can't isolate any one of them. So the idea is that we're working on a way of combining all of this into one function that you can calculate for each compass section looking around at a typical distance where you'd expect the midpoint patch for your first skip ease into Europe might be. So we're experimenting with plotting a sort of a dartboard arrangement where you set your inner limit for your skip distance and your outer limit, not the skip distance, your midway point, and you examine the model data points within here. You've got a lot of the other stuff, and you come up with, once you've loaded the data, you come up with, for your postcode or your locator, probability functions that give you a chance of which direction. And there's a slider along here at the bottom, which you can move. This is now, and you can go back 6 hours if you're checking up a contact you had a little while ago, and you can go forward 6 hours, or 12 hours rather. And you can alter the distance of the radial rings. So that's where it's going to next. So these are all ideas that come about through the observations that you put into the system. So good on you, gang, for those. If you don't put the things on the cluster, then you don't have enough to base the next generation of these things on. But it's great fun, and yeah, we're working on a new version that will be a site that contains this as a way of getting me out of having to write a blog every morning. Nothing wrong in that. So that, I think, is the end of my piece, and yeah, Chris Ian is back on.
Chris Ian. Yes, actually, it's Christine at the weekend. Oh, hang on.
Oh,
Is it on?
should be.
Yes, you can hear me. Hello. Right. Yes, okay. So I gave a talk on this last year, and I dare say quite a few of you were there. So I'm not going to go over all of that, but I will repeat some. So the motivation for this is experimental work. It's just trying to find out what goes on. Curiosity driven, if you like. Because we are blind to a key characteristic. Most of us, most of the time, are blind to a key characteristic of the radio waves that we're using, and that is their polarization. We all use horizontal polarization for most things, but that's partly purely practical. There is actually a small ground gain factor as well. But over the years, it's become the norm. But it's much easier to put up an antenna that's horizontal beam than a vertical one. But the hypothesis that, if you like, I was got in my head is that, as Jim was describing, the sporadic E layer is a concentration of ionization. It's squeezed together, makes it very dense. And if you were to look at an ionospheric radar, an ionosonde, looking straight up, you would see that whereas the radio waves go through the F2 layer for a fairly long period, it's much quicker and sharper with the sporadic E. So does that mean that it's different? On HF, we're pretty used to the idea that the polarization of the incoming wave is scrambled. It's all over the place. I just wanted to find out whether the same thing applies on 6. So that's my antenna. That's a key part of the experimental setup. These two here, there's two swallows. We have them nesting in the garage. So across Yagi, you have to have a non-metallic pole, otherwise it gets in the way of the vertical one, and you have to feed the coax out the back in case that gets in the way of the vertical one. So most people won't be doing this because it's somewhat specialised. But that's what I've got. It's a 7-element INNOV antennas, 30 foot long, 20 metres up. Using an SDR, that's an HP SDR screen. Anybody who's using an ANAN, which is what this is, will be familiar with that. And essentially you've got two parallel receivers, one on the horizontal antenna, one on the vertical antenna. And one of the nice features of this software is that there's a data collection utility built into it, actually called the radio astronomy feature, which is what it was designed for. But it actually allows you to track the signal strength very fast. In fact, I sort of run it as fast as it'll go. So this is a real SSB signal on 6 meters. This is actually this first set of measurements. I should say that basically I'm going to replay some of the first set of measurements that I did, but then I've been doing something different this year to tackle the same question from a different angle. So the black is he was actually, I did email this guy afterwards to find out whether he was running a horizontal antenna or not. Of course he was. But you can see that the black signal, which is the horizontal, goes through an enormous fade in the middle. And if you were trying to work this guy, if he was somewhere slightly more exotic than IS0, he would have virtually disappeared. And you've no way of knowing whether that's because, well, you assume that it's just faded out. But what's actually happened is that the vertical signal was there. His signal turned vertical in terms of polarization, pretty much. And this happens a lot. You can actually work out then what the angle, the effective net polarization is, assuming that it's not really linear polarization, it's almost certainly elliptical, but you can work out what it is. So this is over a period of 200 seconds, so what's that, 3.5 minutes? Ish. And so you've got 0 degrees, i.e. horizontal at the bottom, and you've got 90 degrees, i.e. pretty much vertical at the top. And you can see that it's, in this particular case, it's varying over this sort of cycle. And it goes all the way from being virtually horizontal all the way up to being virtually vertical. By the way, if it's elliptical, this sort of shows that actually if it is elliptical, it's pretty narrow. It's a pretty narrow ellipse that you're looking at, or at least at those points. Here's another one. This is actually I0JX, a well-known beacon. Beacons are better because they transmit all the time. And I0JX is on a vertical antenna. So not surprisingly, and this is one of the things I'm interested in, is on average, even though it varies up and down all the time, on average it's more, you can see that from the red. The red is vertical. The black is horizontal. It's more vertical than horizontal, but it's certainly not just sitting there like that. This is why you can actually work perfectly well on Sporadic E using a vertical antenna, because half the time it's not vertical. It's not horizontal, rather, when it's coming in. So this is working out the polarization just for a section in the middle. So this is only 20 seconds here, but it's fairly typical of what you see, that and these are the individual measurements. They're about 15, 16 measures a second on each channel. So it's fast, but you can see there's a sort of a way. I got told off yesterday for saying this wasn't chaotic. Apparently it is. In a mathematical sense, yeah, it can be described as chaotic, but it's certainly not random. Now, interestingly, that BBC paper that I flashed up earlier actually said, and the polarization's random. It's not. It doesn't always have that kind of period. It has periods between seconds to a minute-ish sort of thing. Doesn't always do this. There are times when other factors happen, but it's and that's consistent with an elliptical polarization rotating. And by the way, it's pretty elliptical, otherwise you'd never get up there. And you don't get round down there. So that's what I was doing last year. And I will go back to that because there's some information there that you won't get anywhere else. This is another extract from that BBC report that I talked about, and they actually did, between some of the paths that they monitored in some years, they ran vertical and horizontal polarization because they wanted to find out whether by cross-polarizing the antenna you could reduce the incidence of sporadic E interference. That was their motivation for it. And what their results found was that, and these are, without going into it, this is how much stronger the horizontal, or rather the transmitted polarization was on average relative to the vertical. It's very smeared out. It's like one of Jim's, or Fred, as we otherwise call him. It's averaged out. But you've got, you've got a Jesu S point there. So, apart from one path, interestingly, they were doing a range of frequencies too. By the way, the incidence of sporadic E, the difference in the incidence, I didn't put this one on the chart actually, between the 40-something megahertz of the lowest frequency, which was the bottom of band 1, up to 58, didn't vary much. So those of us who might worry about, if I go above 50.3 for my FT8 contact, I will miss the sporadic E, it's not true. It varies, but much more slowly than that. So, speaking of FT8, I wanted a way of looking at a lot more paths, because the trouble with the beacon is there's only a few of them. You have to watch out for when there's actually an opening to that particular beacon, and you have to set the thing running, and then you have to analyse the data and so on and so forth. And I wanted a way of really finding out whether that's true, because I must say that I sort of expect that. From experience seems to suggest that because most people are transmitting horizontal, there's a bias towards the horizontal. We know it's varying, but there's a bias towards the horizontal. So, I want to find out whether that's true or not. And I did it using WSJT-X. So I was running 2 instances of WSJT side by side from my desktop. I did both JT65 and FT8. FT8, obviously, it's quicker. It takes more samples over a 14-second period, whereas JT65 does it over about 50 seconds. So, and of course, every message, it tells you that I was receiving that station on that frequency at that point. Also, I can see that K1PI was working I7IX. Also, that K1PI, the signal-to-noise ratio was -2 dBs. And it's an estimated signal-to-noise ratio, but it's an average over the whole measurement period. And one of the features that WSJT-X has is that it will record all of that into a log file, into a text file. So what I was generating, effectively, was 2 text files. It's a bugger to try and align the two together, actually, when you're analysing the results, but it takes quite a long time. But nonetheless, so it was tracking 2. And I've analysed a couple of events, couple of sporadic E events. And the first one was using JT65. So a relatively small number of results, data points. And interestingly, you can see, oh, hang on, there's another bump down there. So you've got a sort of an average in the sort of middle of the range. The thing's rotating all the time. You'd sort of expect it to average out. But there's a bump down here in the horizontal end. But then, of course, that's actually the tropo signals. So I stripped out everything that was less than 750 kilometers away, which is fairly long for tropo, but this mode can detect some very weak signals. So I did that, and then you get that picture down the bottom. So it's sort of smeared it out, and you've got a more even distribution. But I wanted to do something which was both faster and gathered more information, more data. So you probably can't see the numbers on there, but that's a different opening. This is an opening to Eastern Europe. over an 8-hour, at least I was monitoring over an 8-hour period. I think actually the opening was a bit shorter than that. And there are about 2,100 data points in that. It's really efficient for gathering data. And obviously I'm using signal-to-noise ratio as a sort of a proxy for the actual signal strength. That's the only weakness of one of the weaknesses of this. The other weakness, actually, while I think of it, is that one of the measurements I had to exclude were the situations where one of the antennas detected it and the other one didn't, which probably means the other one was there, but it was just too weak to be decoded. And what that means is that if you're like pure horizontal and pure vertical, it's not going to show up in this data set because I've got to have two numbers, otherwise I know nothing. So it probably underestimates what's going on at that end and that end. And you'll see that the average, mean, median, whichever one you want to use, angle is about 40 degrees. So this is already telling you that although it's varying on a short time frame, on average, it's looking, well, it's either circular or it's like that. You know, so this is actually supporting the idea that the polarization of the wave is rotating constantly or changing constantly. But then, those of you who were here last time, remember that John spoke almost as much as I did, and one of the points was around ground gain. Ground gain. Now, I sort of ignore ground gain on the other one because actually I could sort of calibrate it out, and also well, whatever, the vertical and the horizontal, it only made a tiny difference in terms of the polarization angle anyway, to be perfectly honest. But I wanted to find out whether it had an effect here. And the fact is, particularly if you look at the left-hand one of these graphs, that the horizontally polarized wave, when it's hitting the ground, there's a phase change. It changes by 180 degrees. And that gives you one sort of pattern. The vertical wave over, this is a perfect ground, so this is a perfect conductor. It's theoretical, does not have a phase change, and so actually the maximum, this is the fabled, you know, you have your vertical antenna on HF and the radiation is right on the horizon. The thing about this is that the vertical and horizontal are completely out of phase with each other. So doing the sort of measurements I've been doing, if that was what was really going on. So this is just a chart of ground gain here. Sorry, if you can't see it from the back. There's the 0 point. So you've got up to 6 dBs of gain, extra gain, by being close to the ground, which is how we managed to work the odd EME contact on 6 meters. Most people who work EME are doing it near the horizon on 6. But, you know, your first maximum on the vertical is actually in the minimum on the horizontal and so on and so forth. So you really can't compare the measurements at all. But that's not realistic if you're not on a perfect ground plane. And over average ground, because of the conductivity and the electromagnetic effect of the non-perfect ground. And by the way, this particular direction from where I live is definitely not perfect. It's housing and trees and God knows. You have a much more the horizontal one is still got a fairly sharp node actually, but the vertical one does not. And there's about a 2 dBs difference in this bottom range. And for a 1,500 kilometre path, those the Beacon and the IS0 SSB station were both at around 1,500 kilometres from here, from my location. So, and that corresponds to an angle of about 4 degrees. So you've got a difference of 2. But what it does mean is that there's a point here where you're risking under-reporting the horizontal stuff because there's potentially quite a node there, a gap, a reduction in sensitivity of that's minus 20. So what I did then was to that previous graph chart, I put a ground gain correction of 2 dB on the vertical, and I removed everything that was under where the angle on the ground would be less than 7 degrees, which is about 1200 K. So this is virtually my last chart. I can see the chairman getting wanting me to shut up. And miraculously, and I didn't fiddle this, honest, It's come to 45, and that sort of makes me feel as though it's right. Perhaps I shouldn't. Perhaps it shouldn't feed my preconceptions that way. But so there's a big spread once you make sure that you're talking about single hop. By the way, I had to delete. There were some records in there of graters that were double hop, and get rid of the tropo, and actually get rid of the shorter range sporadic E as well. So that's where I've got to on this. It seems to show the BBC were wrong. Not quite. Maybe they didn't take account of the ground gain. I don't know. There you are. So the average polarisation over a 14-second period, chaps, of your 6-metre waves, whatever you've transmitted, is going to be at 45. So just bear that in mind. I think next I'm going to go back to the other stuff, the faster records, and see what we can find out about that. So that's where I've got to. Just an update. Conclusions, well, you can read this. These are but more or less what I've been saying. It does happen on 2-hop and 3-hop E's. I've got some pictures of that, which I showed last time. It tends towards 45 degrees. The variation, well, there you go. You can read. And auroral signals generally come back the way that they were transmitted, interestingly. So I think that's me. Yeah. So thanks very much, and over to our chair.
All right, thank you very much, Chris. We actually have time for a couple of questions. So who would like to grill Chris, Fred, or whoever else was talking?
Hey.
Oh, yeah. Any questions, please? Goodness me. How am I going to get the microphone up there? Yeah, we're going to need it back. Here we go.
Yeah, Chris, if the average polarization angle is 45, and we're assuming, let's assume we're transmitted horizontal and that's 0, the other results that you've quoted suggest that there's a bias towards horizontal, and therefore the polarization angle should be somewhere between 0 and 45.
That's exactly what I was testing.
So
the point is that when you average over a larger data set, it's not.
So why is that then? That's my question.
No, I mean, why would it be biased to the horizontal? I mean, that was the perception, but why would that be the case? I can't think of a sort of, I mean, an aurora is a bit different, obviously.
Aurora is very fundamentally different from this. All I would say is that from the EME experience of playing with the ionosphere is that you're not losing the horizontal, and I don't think you're losing the horizontal and you're losing the vertical in either case. You're ending up with very mixed polarization, elliptical as you say, but actually I think you're seeing deformation of the ellipse. In other words, it's not swinging round in its vectors so much, but it might be squeezing in and out.
But that means the net polarization is rotating. Yes.
But yeah, no, you're absolutely right. In fact, there's something I didn't include last time that I did show before was what some recording of Graham's use it on a beacon using litigious figures to show the actual sort of shape of it.
Okay. I've got to do one more walk for the last question because I get told off if I don't keep to time.
It's a question for Jim. The correlation on those 5 years, would that have anything, or have you thought about the El Nino and La Nina effect? And also, another question is, these blocking high pressures, they seem to be having an effect on the jet streams. I don't know if that's relating anything to do with global warming and whether we'd see more incidents, but I just seem to have become aware of the weather people presenting more of these blocking high pressures. Presumably that's holding the jet streams in certain ways. And if that happens, do you think that, therefore, might increase the incidence of these sort of sporadic E paths to JA that we're seeing?
Yeah, it is a related thing in the sense that to get the blocking highs, you tend to have a much distorted meridional north-south type of flow. So in other words, the one is the cause of the other. So if you hear in weatherman speak, weather girls speak on the telly, people talking about we've got a very blocked weather pattern or so on, that's our speak for saying it's very meridional. The propagation westwards of the wave pattern isn't very great, and these patterns hang around. The beauty of it is, Chris's periods that he identified, and looking back through the logs in the comics, you find that when you get past to JA, I don't know if it's a common observation, but you notice that it happens usually over a few days at a time. It's not usually an isolated day, but it's over a few days consecutively. And that can be also symptomatic of when you get these, the extreme blocking pattern is actually what we call in the trade an omega block, when the jet stream forms the Greek letter omega. And that's hugely difficult to shift. So it virtually, some of you will remember the 75-76 drought. That was an omega block in the upper pattern, so nothing shifted things through. But it does imply this very meridional fixed thing. So if you get an opening on ease to wherever, it applies over the Atlantic side to over the Eurasian side as well. Same principles apply. As for the La Nina, El Nino thing, that's more a Pacific thing, but it does have some knock-on effects over the flow over the Atlantic, and it's not absolutely clear what that implies for this. But basically, look for blocked patterns. And if you get a very strong jet stream propagating out from the states across the Atlantic, very often the instability inherent in that will cause it to distort and eventually buckle and produce these very meridional patterns. So you then look for developments of these multi-hot paths to the Caribbean, to the States, or to South America on 6, or the other way towards Asia.
Good. Thank you very much, Jim and Chris. Can we thank them again in the usual way? And guess what?